Question 18C. The figure below shows a rectangular loop of wire with dimension L by W that lies in the plane of the paper. A long straight wire also lies in the plane of the paper and it is at a distance d from the rectangular loop. The current through the wire varies according to I equals 1.5 1 minus beta t, where beta is a positive constant and time t is measured in seconds. What happens to the magnitude of magnetic flux through the rectangular loop for the following cases? In what direction is the magnetic flux? In what direction is the induced magnetic field in each case? Use Lenz's law to explain your answer. So here in this question, you have a rectangular loop which lies in the plane of the paper, and you have a straight current carrying wire that carries a current of I equals 1.5 1 minus beta t. I need to find what happens to the magnitude of magnetic flux through the loop, what is its direction, and what will be the direction of induced magnetic field in these two cases. So let us start with case 1. Now beta is a positive constant. That means value of beta must be greater than 0. And in the first case, beta t has to be less than 1. If beta t is less than 1, that means my time value must be less than 1 over beta. So let's say if I choose beta to be equal to 0.12. Now this is something I have chosen by myself. It has to be a positive constant, so it is greater than 0. And since beta t must be less than 1, the value of beta must be less than 1 as well. Only then the product will be less than 1. I need to determine what happens to the magnetic flux through the loop. Magnetic flux through the loop will depend on the magnetic field generated by the wire. And magnetic field generated by a straight current carrying wire is given as P equals mu naught I over 2 pi r. So it is basically directly proportional to the current I. So I need to know what happens to current I with time t. Only then I can determine what happens to magnetic flux and the magnetic field. So let us determine the current values for certain time values. But what values of time are possible in this situation? Whatever time values I take, I have to ensure that those values are less than 1 over beta. The beta I chose is 0.12. So the time value I should choose must be less than 1 over 0.12, which is equal to 8.33 seconds. So I can only choose the time values which are less than 8.33 seconds. So let us take some values here. I will take my time going from 0, 1, 2, 3. 4 values of time is enough to determine what happens to the current. Then we calculate what is beta t for this time value. All you have to do is multiply beta with the time t. So beta times 0 will give you 0, times 1 will give you 0.12. This will become 0.24 and this will be 0.36. All I did was multiply 0.12 with the time values. Now let's see what happens to current I. I'm going to substitute these values of beta in the expression for current. So time t equals 0, I have current as 1.5. At time t equals 1, the current becomes 1.32. Then we have 1.14 and then we have 0.96. So you see, as the time goes from 0 to 3 seconds, the value of current is decreasing. And if I is decreasing, magnetic field which is directly proportional to the current will also decrease. So we say magnetic field through the loop is also decreasing. Now if magnetic field is decreasing, phi, which is VA cosine theta, the magnetic flux, also has to decrease. So now we understood what happens to the magnitude of the flux. Since the current is decreasing, magnetic field is decreasing, and hence the flux is also decreasing. Next part of the question is asking you what is the direction of magnetic flux. Now flux is a scalar quantity. You get magnetic flux as a dot product of two vector, which is B bar dot A bar. And since it is a scalar quantity, it has no direction. So we cannot determine the direction of magnetic flux, but we can say whether it is entering the loop or whether it is coming out of it. We can say that it is positive or negative depending on whether it is entering or leaving. Now, how do you determine if it is entering or leaving the loop? So magnetic flux is defined as the dot product of two vectors, phi is B bar dot A bar, which you can also write as BA cosine theta. So if the angle between magnetic field and the area vector is zero, if they are both in the same direction, we say that the magnetic flux is positive and it is coming out of the loop. But if the angle between them is 180, if they are in opposite direction, we say that the magnetic flux is negative because cosine 180 is -1. So how do we determine the direction of field and area vector in this situation? First, we determine the direction of magnetic field due to the current. The current is going up. It is decreasing, but in positive direction. So you use the right-hand thumb rule to find direction of magnetic field here. Magnetic field due to a straight wire has to be in the form of circular concentric loop. Point your thumb in the direction of current. The fingers will give you the direction of magnetic field. So in this situation, magnetic field is going in counterclockwise direction. And since it is going in counterclockwise direction, when it approaches the loop, it is going into the loop. So here, direction of magnetic field is into the loop. I will call this as B original, the original field because of the wire. Now, what is the direction of area vector? Area vector always points out of the surface. So since this loop lies on a paper, I will show my area vector coming out from the plane of the paper perpendicular to it. So direction of area vector will be coming out of the plane. So you can either show it with the help of a dot or coming out like this. This is my area vector. So in this situation, if you notice, angle between magnetic field and area vector is 180. They are opposite in direction. And if they are opposite in direction, we say that the flux is negative. So magnetic flux here will be negative. It is entering into the loop. So I cannot comment on the direction of flux as it is a scalar quantity, doesn't have direction. But if you were to speak about in what direction magnetic field lines are going, as flux is defined as the number of field lines passing through a surface, you can say that the field lines are entering the loop, or magnetic flux is entering the loop since it is negative. Next, we have in what direction is the induced magnetic field. Now, according to Lenz's law, induced magnetic field opposes the change in magnetic flux. And how do you determine the direction of this induced magnetic field? If your original field is increasing, you induced magnetic field in the opposite direction. So whichever direction your original field is, if it is increasing in magnitude, you induce the magnetic field in opposite direction. Then, if your original field is decreasing, you have to induce magnetic field in the same direction. And this is because of Lenz's law. The purpose of induced magnetic field is to oppose the change in flux. So if the magnetic flux is increasing, the loop doesn't want that increase. And in order to keep the magnetic flux steady, in order to keep it constant, it induces the magnetic field in the opposite direction to cancel out the effect of any increase in flux. Whereas if the magnetic field is decreasing, that means the magnetic flux is decreasing, the induced magnetic field opposes that change. It doesn't want the magnetic flux to decrease, so it induces a magnetic field in the same direction to compensate for that decrease. So remember this rule for Lenz's law. B original increasing, induced in opposite direction. B original decreases, induced in the same direction. So in our situation over here, since the current is decreasing, magnetic field is decreasing, and hence the flux is also decreasing. So we have to induce the magnetic field in the same direction as the original field. So I can write here B induced is also in the same direction as the original field. So B induced is also into the loop. Now let's look at the next case. In the next case, beta t is greater than 1. Beta is still a positive constant, so it has to be greater than 0. And if beta t is greater than 1, that means time t can only take values which are greater than 1 over beta. So in the previous part, I took beta to be equal to 0.12. And if I use the same value of beta, I can only take the time values which are greater than 1 over beta. That means 1 over 0.12. This gives me the value of time to be greater than 8.33 seconds. So now when I'm determining what happens to current, I can only take time values which are greater than 8.33 because my case is valid only for those time values. So let's do the same process. I want to determine what happens to magnetic flux. To know what happens to magnetic flux, I need to know what happens to magnetic field. And I can only know what happens to magnetic field if I know what happens to current. So let us determine what happens to current when time values are changing. So again, we will take some time values, but this time the time values must be greater than 8.33. So I can take my time values to be 9, 10, 11, 12 seconds. Then I will find what is beta t for these times. We just multiply the value of beta with time t. So for 9 seconds, we get beta t to be 1.08. This has 1.2, 1.32, and 1.44. Then we find the values of current for these times. All you have to do is substitute beta t in the original value of current, which is I equals 1.5, 1 minus beta t. So these beta t values I will substitute here. You get current to be equal to negative 0.12. Then this is negative 0.3, negative 0.48, negative 0.66. So you will notice here that the current has changed its direction. It has become negative now. It is negative, but it is still increasing. That means when beta t is greater than 1, current has reversed its direction and it is increasing in magnitude. So instead of going up, right now my current is going down like this. It has reversed its direction. It has reversed its direction, but it is increasing. So I say that I is increasing, but in opposite direction. Next, we know that magnetic field due to a straight wire is given as mu naught I over 2 pi r. So this magnetic field is directly proportional to I. If current is increasing, magnetic field is also increasing. And if magnetic field is increasing, magnetic flux through the loop should also increase. So we now determine what happens to the magnitude of the flux. Since magnetic field is increasing, magnetic flux also has to increase. The next part is asking you about the direction of magnetic flux. Again, magnetic flux is a scalar quantity, so it cannot have direction. But we can talk about whether it is entering the loop or whether it is leaving the loop. Will it be positive or negative? Flux phi is given as BA cosine theta. Depending on whether magnetic field and area vector are in the same direction or opposite, it can be positive or negative. Area vector will always be pointing out of the plane. This is an open loop, but it is kept on a paper. It's in the plane of the paper. Area vector we will take coming out of the paper. And magnetic field in this situation, the current is going down. So you can show your magnetic field using right hand thumb rule. Point your right hand thumb down and your fingers will curl in clockwise sense. So magnetic field is going clockwise. And at the loop, magnetic field will come out of the loop. So we can show fields coming out in the form of dots. So here, since both magnetic field and area vector are coming out, we say that the flux is positive. It's positive because the angle between them is 0 and cosine 0 is 1 and you have a positive flux. So we can say magnetic field lines are coming out of the loop or magnetic flux is coming out of the loop. But technically, magnetic flux has no direction. It is a scalar quantity. It is a dot product of two vector, which is a scalar. So it does not have direction. But we can say that magnetic flux is positive because both magnetic field and area vector are in the same direction. And since the field is pointing out, the field lines are coming out of the loop. Next is, in what direction is the induced magnetic field? Lenz's law says that induced magnetic field will oppose the change in flux. And if magnetic flux is increasing, it is increasing because magnetic field is increasing. And like we discussed before, if magnetic field is increasing, we induced magnetic field in the opposite direction. So here my magnetic field is increasing outward. It is coming out of the loop and it is increasing. If it is increasing, I induce in opposite direction. So induced magnetic field will be into the loop. So this is how you can determine what happens to the current and hence magnetic flux and induced magnetic field when you have a current carrying wire next to a loop.